So I will use this time to present our work about hydrogen storage material. So I'm sorry that I have made a little bit how to say changes in our presentation, since in the program book may be different title like this, but still in hydrogen storage material. So in this work we would like to show you the using of this nano silica we produce from local rice husk atau abu padi. Kita campur-campur sikit bahasa Melayu ni. Jadi okay. So here we will put this nano silica in magnesium hydride for hydrogen storage material application. So this the background, and then you know maybe some of this the fuel cell. So to go to this application, we have around 3 road: production, storage, and mass production. But to mass production road, we have suitable storage. So here, if you want to use hydrogen in fuel cell, so we have 3 types of storage: in gas, liquid, and solid. Okay, we already have maybe 4 presenters in theoretical presentation. This 100% experimental work. So we focus on solid state hydrogen storage material, since we can store hydrogen in atomic structures and also release hydrogen again when heated, and we can put at room temperature. This is the correlation between gas storage, liquid storage, and solid storage. So we can reduce the volume of solid state between this type of storage. And then, okay, I skip this one. In research and development of hydrogen storage material, we have 4 types of hydrogen storage materials, and we focus in this one, the simple metal hydrides, magnesium hydrides. Lanthanum nickel 5, I think in a couple of years, people already dispute this one. And what is problem with magnesium as candidate material for hydrogen storage? We have high hydrogen capacity, 7.6 weight percent, since IEA, International Energy, have put a target for 5 weight percent. So this is suitable for hydrogen storage material, and lightweight and also low cost. But unfortunately, we have problem with this one, since magnesium work up to 400 degrees Celsius, and also very low kinetic of hydrogen reception. I mean, if we dissolve and absorb for 7.6 weight percent of hydrogen, it takes around 1 hour, minimum 1 hour. So IEA have put the target minimum around between 10 minutes. So we would like to reduce the hydrogen disruption temperature and also the kinetic of high hydrogen disruption within 10 minutes. So how to overcome this problem? And then some people give some approaches like using novel methods like mechanical alloying. We work with this one, and then also adding some alloying element like normally transitional metal. And then in this one we show you using a suitable catalyst, metal oxides, metal oxide. Okay, let's switch on. So if you use a metal oxide, normally how to say, import from other countries. So here we want to purification the silica from rice husk, abu padi. Paham tak abu padi? Jadi here we would like to show you about our high energy ball milling in our laboratory, and then Here normally people work with this milling file, and then we produce a new type of milling file. We can work in vacuum. So here in air, and then with this new type we can work in hydrogen maybe for 10 to 100 bars. So here will be some of our experimental. About the silica itself, some people work in this silica for hydrogen separation, and here Norton and his friend already show a silica nanospring in hydrogen storage material. So this is our motivation to work in this field. So and okay, this is. We have extracted the silica from rice husk, local rice husk, and then we can produce the purified of 97%. Then this silica we put in magnesium hydride, and we use a ball milling to mix all of this material. And then we found here that magnesium hydride is dominated in the magnesium hydride plus silica as catalyst, and then what we found here that around maybe 1% was a problem with magnesium oxide. Since we would maybe from 10% sample to rotary ball mill, it was oxidized. But if we calculate the crystal size of the material, it was about 106 nanometers. And then this is the important thing, that after we produce the material and then we check the thermal properties, that for 1% of silica, after 5 hours of peeling, we have the deception temperature 340 degrees Celsius. It already decreased because the pure magnesium hydride has 420 degrees Celsius. We can reduce this around 100 degrees Celsius. But if we put 5% of silica, also still in 5 hours of milling, and then we can reduce a little bit of the deception temperature. So here we can make some little summary that nanosilica was successfully extracted from local rice husk by co-precipitation method, and then we can have the deception temperature that the lowest is 338 degrees Celsius within 14 minutes. So we can work in 14 minutes. If we use pure magnesium hydride, it would around 1 hour, 60 minutes. So we can reduce to 14 minutes. But the problem still, the highest of hydrogen, the deception temperature, because IEA has put the target below 100 degrees Celsius. Okay, thank you.
Thanks to Dr. Zulkarnain Jalil for very nice presentation. Any question, comment? No question? So I have a question. But the thing that's interesting to me is how do you extract the silica from hard ice? So what I mean is the procedure, the step by step to get the silica. Could you please explain?
Okay, we use co-precipitation method. It's totally chemically work. So we use HCl. We use HCl, NaOH, and then some others chemical materials. So in this case, we use magnetic stirrer to stir all of the material in various of NN, LPM, and then after that we have gel. After we have a gel, we wash with aquades, and again we stir it for 1 hour, and then we use a furnace on 70 degrees Celsius. After that we have the precipitation atau endapan. This is the silica, and then we check with XRF, which on 97%.
What about the ball milling?
We use ball
How
milling.
is it?
We use ball milling to mix magnesium hydride and this silica. But normally people in others group, they work up to 80 hours to mill this one. But by using silica, we only work in 5 hours. So I think it's efficient time.
Thank you. Any question? So if you have no question, let's thanks again to the speakers.